I'm thrilled to be invited to give a talk in this seminar. My talk today will be on reservoir computing, which was very popular a few years ago and is apparently less popular now, but I still think it's cool. So we're going to be talking about reservoir computing today. So where can I change my slide now? There we go. Sorry, my laptop is baffling me. So for those who are joining us who are maybe new PhD students and were not around computing became popular, I will just recap a little bit. So this paradigm was independently developed by Jaeger and Mars, who called it slightly different things, but it amounts to the same thing. So in both cases, you have an input signal, which is driving a static recurrent network of something. So in our case, neurons, but it could be anything. Anything that has a nonlinear component. So it could be a bunch of nonlinear springs, or it could actually be some fluid or something. And then this projects to an output. And then we have a linear regressor on the output, which is trained on the observables of your reservoir to approximate a desired input, desired output even. And the key behind this, the key principle, is that the input is being expanded in a nonlinear way. I have some noise on somebody needs to mute the microphone, please. We are expanding the input in a nonlinear way to a higher dimensional feature space, and then we can linearly combine those features to minimize error. And two properties that the system has to have in order to be a reservoir computer is that it needs to have the separation property, which means that different inputs will be projected to different places in the output space. You can distinguish between things. And you need the approximation property, which is the ability of the readout to approximate, to produce a desired output. So can it actually give the output that you want? So why do I like reservoir computing? What's appealing about it? So first of all, it's a nice match to cortical dynamics. You can have a system that is just bubbling away in a sort of happy non-linear way. It looks at the behavior of a reservoir computer, as we can see in this top right raster plot from one of the seminal studies on reservoir computing. We would look at that and think, yes, you know, this could be cortical neurons. They're asynchronous, they're irregular, there's some sort of oscillations going in there, but it's not a very artificial, blocky activity. It seems like a good match. And also the paradigm doesn't make any unrealistic requirements on the cortical structure. It doesn't require all-to-all connectivity or strictly feed-forward connectivity or anything like that. So that's nice. It can handle inputs with continuous time, and therefore the tasks that have some temporal structure to them. And we don't need to learn the recurrent weights with some biologically implausible learning rules. We can leave those static. And that's also interesting if I get time to move on to neuromorphic computing. If we can avoid training recurrent weights, that's a very nice thing for a neuromorphic system. So having said all that, what don't we like about the reservoir computing paradigm? So for one thing, it's not clear how the output can be made useful in a biologically plausible way. So in the classic reservoir computing scheme, we have these output neurons which are trained by supervised learning. So we need some kind of training signal there that knows what the answers should be. And this is always a little difficult to justify in a model of how the brain works. So ideally we'd have something else there. It's unclear also how the biological features of the network influence its properties. So if you can see this table here, again from the Heusler and Mars paper, they set up their network with varying different assumptions on the connectivity, and they could see that if they have the laminar cortical structure, then this network is better at doing the tasks than a network that's got small world connectivity or that's got completely random connectivity. So it obviously matters, but we don't really have a clear idea on what matters and why it matters. And in order to get there, in order to understand these things, we'd like to be able to quantitatively compare the properties of networks. And that's also been a problem generally, because we can do benchmark tests on them and say, okay, can this network, how well does this network solve the XOR problem? How well does this network solve the classification? But we can't look at this in any kind of systematic way. It's more like just samples of the computational ability of the network. So I'm going to go into these three problems in a bit more depth, starting with the last one. So how can we quantitatively compare them? And there was this very nice method that was developed by Debra in 2012, which was designed for discrete systems, or formulated for discrete systems, and it works on the basis of creating orthogonal target functions, and then we can see to what extent can we reconstruct those target functions. And the key thing here is she uses Legendre polynomials, which are orthogonal, and then we can create target functions that are products of these polynomial functions, and not just the underlaid polynomials, but also including some delay. So we can build up. Here are some examples in the bottom here. So we can say we want a target function which has a delay 3, a maximum degree of 3, and a delay of 5. And one way of doing that would be having the polynomial of degree 1 underlaid times the polynomial of degree 2 with a delay of 5. So obviously we can make many of these that fit into that category. It's a combinatorial explosion. But the nice thing about this is that the ability to reconstruct those decreases monotonically. So if we reach a point where the degree n is already not very well reproduced, then we don't have to go and look at n+1. So what we do is that we can create all of these functions, starting with the simplest, the lowest degree, the smallest amount of delay, and increasingly increase the complexity and the delay until the system just can't do it anymore. And for each of these target functions, we can by training a readout for that particular function, we can say how well does it reconstruct that, and then we can make a sum of all of these reconstructions, and this gives us something like the total capacity of the network. So when I said in my abstract that this is a method that you can use without training on tasks, that was obviously a lie, because there is some training involved, but it's training in a very systematic way for polynomials that can be done offline, and it gives you a more all-encompassing understanding of the capacity of the network, rather than just it can do XOR to this extent, or it can classify to that extent. So over on the right, we can see from Debra's paper, we can see how the total measured capacity, for example, decays as the gain, where's my mouse gone, as the gain scaling parameter increases. So this is the strength of the recurrent weights inside the echo state network. And over here we can also see as a function of the parameter iota, which is the scaling of the input weights, how the capacity profile of the network moves from completely linear over for the small values of iota, and to larger degrees as we increase iota. So if we take this this measurement or this technique, then we can apply it in a systematic way to understand, or at least to get an insight into how the capacity profile of a system can change depending on various parameters. So here, following the approach of Debra, we're looking at the capacity of an echo state network with respect to its recurrent weights and with respect to its input weights. And this plot A shows us the total capacity, so the sum over all of these individual capacities. And we can see that this system, your best total capacity comes when you have a small recurrent weight, and it's not so dependent on the input weights. But if we then look into this in more detail, if we say, okay, but how much are all these capacities weighted, then we can see that it does in fact also depend on the input weight. So if we look at panel B, we can see that the maximum degree of a polynomial that can be reconstructed by the system, that this decreases as iota decreases. And plots C and D give you something like the capacity profile. If we take a slice through these, through a vertical slice through these heat maps in A and B, we can see for two examples how the capacity profile moves from largely linear to include more and more polynomials of higher degree. The ability to reconstruct different delays has a completely different shape. You can see that in plot E, where we can see that for most of the parameter space, the maximum delay is below 100, but for this small area down at low values of iota, then we can suddenly reconstruct much longer delays. And this shows us that the system can be moved into different computational modes depending on how we set the input and the recurrent weight. So we can have, as shown in F, something with a relatively short memory but high nonlinearity, or we can shift it to another area and we can have, as shown in G, a linear system that has got a very long memory. So the computational network, the profile of the network is dependent on these parameters. So just to give us some sense that this is measuring something important about the network, this shows how the maximum degree and the maximum reconstructed delay, how this predicts the ability of the system to do some calculations. So here on the left-hand side, we're looking at the ability of the system to perform an XOR task, which is in blue, or a nested XOR task, which is in orange. And as we increase the parameter iota, and we can see that the XOR is pretty easy, so most of the network can manage that. The nested XOR is more complicated, and we can see that as the maximum degree of the network rises, so rises the ability of the network to calculate this function accurately. And on the right-hand side, we're looking at the same, a similar approach. So again, shifting systematically the input scaling from small values to large values, then the maximum delay that can be reconstructed decreases. And the green curves show us the accuracy of classifying a stimulus that was delayed by increasing number of slots. So the immediate classification can be solved by all the systems, no matter how they're configured. But the further we're looking back, the more it's only the systems on the left-hand side that can solve that. So this was all echo state networks, which are generally much easier to deal with than spiking networks. What we then wanted to do was extend this, nice technique to spiking neural networks. So what we did first of all is we take this, input signal, which is a discrete signal, and we just spread it out into the corresponding step function, and then we can convert it into a continuous signal to use for the spiking neural networks. And we have two approaches for this. One we call the amplitude value. So all neurons that are receiving input, they will then receive an input signal that is more or less depending on the value of the state function. We have a low value here, then they get not much input, and when we have a high value here, then they get a high value input. So fairly self-explanatory. Then we choose another method, which we call spatial value, where we say we transform this u of t into a location. So we conceptually spread our input neurons over the entire possible input space, and then we center the input on that particular neuron with a Gaussian spread. And this is shown in this bottom panel here. And these are two possible methods that we have for providing input to the systems. Of course, there could be more. These are the two that we've looked at. And we can further say, do we interpret this as a direct current to all the input neurons, or is this the rate of a Poisson process that's providing spikes to these neurons? So there are already 4 variants here, and then we will have a look and see whether it makes a difference which of these methods we choose. But obviously, it does make a difference. Otherwise, I wouldn't have gone into such depth explaining about it. So this is shown on the left-hand side. So the left column, A and C, shows for the amplitude value encoding, and the right-hand side shows the spatial value encoding. So there's a lot of information here. Let's start with comparing the solid curves with the dashed curves. So this is gives the noise model used in the network. So we can either have an ongoing random noise provided to all the neurons, or we can have a frozen noise. So we have a particular background spike train for one epoch, and then we just repeat it. Each neuron has its independent one, and it gets repeated for that neuron in every epoch. So we can see that the solid curves always lie above the dashed curves. The ongoing background noise disturbs the system so much that it is inhibited in its ability to reconstruct these polynomials. So if performance is what we want, then frozen noise gives us a much better result. Next, looking just at the solid curves, we can compare the orange one and the blue one, and we can see that the orange one always lies above the blue one. So again, if performance is our concern, rather than say biological plausibility, then the best choice is providing the neurons with a current rather than with a Poissonian spike input. Then we can compare the left column and the right column, and then we can see that the spatial encoding is again basically always better than the amplitude encoding. So if we can convert our stimulus into a more concentrated stimulus for some neurons rather than a global stimulus for all, then again the network does better at distinguishing these things. Finally, looking at the looking at, so if we just concentrate now on the spatial encoding, we can see that the maximum capacity that the network can represent, that it goes down as the spread of the Gaussian that is representing the input increases. So if we want a high capacity, then actually we want a small spread. But it's the other way around for the memory. So if we want long memory, then we need a wider spread. And these simulations and the ones that I'm going to show you next are all done in Nest. So your ideal tool for all of your large-scale point neuron simulation needs. So now we've looked at the encoding method and the noise model, we say, okay, if we're just interested for the time being, then the best one to take will be the spatial encoding with a direct current and a frozen noise model. And this is what we're going to look at then in more detail. So we can see here the heat maps for this particular choice of encoding strategy and noise model for 3 different spreads of the input stimulus. And we can see in the left column is the total capacity, and then in the middle column, the maximum degree that can be represented, and in the right column, the maximum delay that can be reconstructed. And so we can see, for example, that the total capacity of this that can be achieved by the system goes down as sigma increases, but that the maximum delay goes up as the spread increases, and the maximum degree goes down. So this is unlike the echo state network results I showed you. This is not changing anything about the system. We haven't changed the input weights or the recurrent weights here. It's just about how the stimulus is encoded. So we can here again shift the system from largely linear with a long memory to largely nonlinear with a short memory by shifting our assumptions about how the stimulus should be encoded. So here's an intermediate summary. I talked about what's unsatisfactory about the reservoir computing framework, and one of the things was not being able to compare the properties very well. And so we were able to take this method that was designed for discrete time systems, and if you take a little bit of care with it, then you can also apply it to continuous time systems. And it's relatively computationally inexpensive, certainly as compared to training a network on 5 reservoir benchmarking tasks. But as it's one metric, it gives you an easy way to see the shifting properties as you change something about the system. We found that the nature of the background noise and the way that we interclode the stimulus was by far the most important thing about that controls how much computational capacity a network has, more important than shifting the recurrent weights or anything like that. But the results are also sensitive to the choice of the stimulus step duration, so the length of those UT segments, and also the strength of those. And we see that the same network can have a quite different computational profile depending on how the stimulus is applied. So I'd like to now move on from that and start talking about how biological features of the network can influence its properties. So one of the things we looked at recently is the role of heterogeneity. So for this we took a network with 1 excitatory and 2 inhibitory populations for which there was a lot of experimental data available, and we could turn its various heterogeneities on and off, and so we could have them individually or all together. The three types that we looked at were structural, so how many connections does a neuron get and from where? So over on here you see assuming like they all get that a neuron in population A always gets the same amount of connections from population B, and on the right hand side, assuming that there is a distribution that such connections are drawn from. The same with the neuronal populations. So we had data that shows that we have a large range of FI curves. So we can always take the average, which is shown as the dark curve in the middle, draw the properties from the corresponding distributions. So we end up with an array of different FI properties. And again, on a synaptic level, we can choose the strength and the delay of a synapse from a distribution, or choose them all to be the same. And so we played this through. So we had then a variety of different networks. So a homogeneous network where everything's the same, all the neurons are the same, all the synapses are the same, and so on and so forth. Or just structural heterogeneity, just neuronal, just synaptic, and then everything together. So what we found is that over here in plot A, we're looking at the intrinsic timescales of the network, and we can see that including some heterogeneity considerably increases the intrinsic, or the range of intrinsic timescales. Particularly if we have neural heterogeneity, which should come as no surprise. But also the linear memory. So going back to the echo state network results, so the ability to reconstruct something, but at various delays. This again was improved by heterogeneity, especially by neuronal heterogeneity. And this came as a surprise to us because we were expecting the synapses to be the big deal here, but they weren't. Just including some heterogeneity in the neuronal parameters was enough to considerably increase the capacity of these networks. We also recently investigated the role of connectivity patterns in reservoir computing. So if you remember my complaints at the beginning that we need to be able to make the information in a reservoir has to become biologically useful in some way. So the very minimum that we can require of it is that it should be transmittable. So we looked at a series of networks, and we asked the simple question: if I apply stimulus to the first network, can I still identify that stimulus at later networks, 1 removed, 2 removed, 3 removed? So here we are, if we look in this plot here, plot A, we have random connectivity between one network and the next, and below we have a topographic projection, which means that we define topographical areas in each of the networks such that a connection between the orange areas is more likely than between an orange area and the blue area or an area. And then we just investigate how well does this underlaid linear memory, how well does that work? And so I'm not going to go through all these in great detail, but this just shows the accuracy of stimulus identification. We have here 10 stimuli, so we have a chance level of 0.1, and the unshaded bars show the accuracy if I have random connections. And then we can see, okay, so in the network that is receiving the stimulus, I have perfect reconstruction. in the next network, I also have perfect reconstruction, but already in M2, so the third network on, it's down to about 50%, and then at M3, I'm down at chance level. But if we have topographical connections, which are shown as the shaded bars, then we can see that we maintain very, very good accuracy of stimulus detection all the way through until the third network after the input network. So we can see that these topographical connections are very important to allow multi-layer signal transmission. And so the next question, like the next most basic question after can we even transmit the information in the reservoir is, can we do any reasonable computation with the information? So we looked at classification, so that the network has to classify 2 stimuli at once, and also the XOR task. And for both tasks, we can see that the topographic connections are always better than the random connections, but we can also consider which works better. If those streams go into the same initial network, or if they're going into different initial networks, but then they get integrated further upstream or downstream, more to the point. And then we find that for multi-stream classification, then local computation is better than downstream computation, but for XOR calculation, then local is a lot better than downstream. So you can see in these PCA plots in the bottom right, you can see that how well the areas get distinguished for the XOR. And so you can see, so bottom left is with local calculation and topographic connections. Those 4 point bundles are really very well distinguished, and so it's easy for the network to make a correct classification on the XOR. But for the other ones, if we have random connections, then they get sort of squashed in this direction. So it's much harder for them to be distinguished. And we can also see from this that the XOR task is quite a bit harder than the classification. So for classification, we still have 70% accuracy on M3, which is 3 after the input network, but the XOR task is down to about 0.25, so not very good. So another intermediate summary, we talked about comparing the properties. We've done some initial work, at least, into understanding the effect that the biological features of the network have on the reservoir computing properties. So heterogeneity, good, especially neuronal heterogeneity. And the connection specificity is also very crucial for sequential processing. And we can see that connectivity that allows the computation to occur at the earliest possible stage is advantageous. So we can calculate early and transmit the answer accurately. This works better than passing down intermediate solutions and integrating them later. So the final thing that I'd like to talk about in this particular topic is how the output can be made useful in a biologically plausible way. And as we've seen that random output connectivity is not sufficiently informative for computations that require more than one step, that suggests that for best results, maybe the reservoir should also not be isotropic. And we didn't talk about synaptic plasticity mechanisms. So this is the final study that I'd like to talk to you about with respect to spiking neural networks. And here we took a reservoir computing paradigm and we kind of manipulated it somewhat. So normally with a reservoir computing system, the input connections are static, the reservoir is static, and only the output is learned, and that's learned in a supervised way. So here we add some unsupervised learning to the input projections, and instead of learning in a supervised way, which is difficult or often difficult to justify in a biological setting, because if the supervisor already knows what the answer should be, then the supervisor should just go and do it rather than training these other neurons. So we have reinforcement learning, which is more easily motivated. And the plasticity model that we use here is the one proposed by Christian Tetzlaff in 2013. And for the reinforcement learning, we use exactly the same model, but just with a dopaminergic additional factor involved. And the other thing that we're doing here that's different is that within the reservoir, we string connectivity. So we define groups of neurons, and we say that the connection between those ones is stronger, and then we weaken it between those neurons and the other neurons in order that we have the same overall statistics, as was proposed by Rost and by Rostami. So this gives you some idea about how these networks behave. So on the top left, we're looking at a network that has no cluster connectivity, and we're providing it with the MNIST digits, the first three for reasons of running out of computation time. And at the beginning, you can see that the network doesn't respond very much to the different digits, but over time, which is what you can see on the right, the network starts responding in a more specific way to the digits due to the unsupervised plasticity on the input projections. And here in the middle, that shows you the maps that those three pseudo clusters have learned. They're not really clusters, because all that's different is the input. They're not clustered amongst themselves. The second row shows you how the network, which already has these clusters, how that behaves. And even at the beginning, you can see that the clusters are kind of turning off and on in a sort of a random way. But after it's been running for a while, so after 600 seconds, you can see that there's a very clear response to particular digits. And the interesting thing here is that if we now look at what these clusters have learned, you can see they've specialized for particular features of the input. So the cluster 0 has specialized for ones that are tilted to the right, and 7 has specialized for ones that are tilted to the left, which means that the input can be broken down into more easily recognizable subclasses, which of course increases the ability of the network to classify it. So the performance we can see down here, this plot with the colored curves on it. The red curves show if we don't have the unsupervised plasticity, then neither the clustered network nor the unclustered network really learns anything very well. The blue curves show if we have this unsupervised plasticity, then both networks can learn, but the darker curve shows the behavior of the one that already has these pre-existing clusters, and we can see that this network learns faster, has a higher converged performance, and is just generally more robust. We can use exactly the same network, so without adapting its parameters, just plug it into a completely different task. This is the mounting car task. So if you haven't seen this one before, we have here a little underpowered vehicle that is supposed to reach this flag, and it doesn't have enough oomph to get up the hill. So it has to get some momentum by going backwards and forwards. And so the unclustered network can't learn this task at all. But the clustered network, as the task runs, and this is a closed loop task, so unlike the MNIST task, at the beginning, there's no specialization of the clusters. So this time 0, they're all either on or off. But as the time progresses, the the various clusters become specialized for contiguous areas of the two-dimensional space, so location and velocity. And this shows you the kind of the converged state, that a cluster is specialized here for the position in the middle, and so on and so forth. So it hasn't covered the whole space, it's covered what's necessary to solve the task. And then you can see that it goes through a very stereotypical series of clusters in order to solve this. And again, with looking at the performance, you can see that only with the unsupervised learning and, the blue is good, low is good in this case, my mistake, time to goal. So only with the clusters and the unsupervised learning, the network learns to all the ones are either bad or very bad. And I think what's interesting about this is the result of the self-organization. So it's representing the input, but in a way that's self-organized rather than hard-coded. And if you've looked at other spiky neural network models of reinforcement learning, then there's generally the scientist has decided these neurons are representing this, and these neurons are representing this. So this is done in a self-organized way rather than hard-coded, and it's task-oriented rather than environment-oriented, and it's compact rather than comprehensive. And I think this is rather nice, and I think this is solves this goes towards solving a problem for reservoir computing, but also for reinforcement learning with regards to how to represent the input. So this brings me to my almost final summary. So the last point I looked at was how to make the output useful in a biologically plausible way. I showed you that topographic connections can substantially improve signal transmission. And if we also have unsupervised plasticity and cluster connectivity, then this allows parts of the reservoir to specialize for different input features. And in my opinion, this creates a usable substrate for a more biologically plausible reinforcement learning approach. So it's not in my nature to be entirely positive about things. So I've found some new things to be unsatisfied about. What I haven't really discussed here at all is the relationship between dynamics and computational capacity. And believe me, if I had something clever to say on this matter, then I would definitely have said it. But so far, we are very perplexed about this. So looking at things like the edge of chaos has not helped us so far, or looking at spike statistics, or anything so far, anything we've thought of has been really uninformative. So I remain perplexed about this. Another thing is, so in this last study I showed you with the cluster connectivity, so I'm on the fence as whether this still counts as reservoir computing. So we still have a reservoir, but due to the clusters, ultimately it's behaving in a different fashion. So does this mean that my idea about reservoir computing should be expanded to include this? Or does this mean that I should be considering this as some distinct concept? And my final thing to be unsatisfied about, if you will humor me with a couple more minutes, is how to exploit these findings for neuromorphic computing. So reservoir computing is also interesting as a possible neuromorphic application because there are many physical systems that could provide the basis for this nonlinear but controllable behavior. And some of those are very interesting because they would be, for example, really low energy, and it would help us do computing much more cheaply. So to investigate the possibility of this, we are in collaboration with some people who work, I'll show you their pictures later, but people who work with spintronic systems. We've been looking at the damped and input-driven Fermi-Pastor-Ulam single model. And what's nice about this is that it can serve as a toy model for any system of oscillators, and where you've just got nearest neighbor interactions. So what we have basically here is an elastic string, and then we identify points on the string. And so for each of these points, we can say where is its location and what's its momentum. So we can deform the string and then let it go, and those individual nodes will oscillate backwards and forwards. And then we can use this two-dimensional, the two dimensions of each node as the observables of the system, and we can treat it as a reservoir computer in that fashion. And what we have here, in addition to these, the ideal system has no damping, but we add a damping term, and we add an input drive, which is how we can apply the stimulus to it. And there we can see for a simple system that how the system evolves, that we end up having from a simple oscillation, we end up having power in different frequency bands. This is a cool system. It was one of the first ever to be investigated using a computational approach. So we can apply this method for calculating the computational capacities to this kind of system as well. So if we can convert it from discrete to spiking, then converting it from discrete to continuous but not spiking is actually easier. And here we can see as well that this is looking at a system with 50 nodes. And once again, we can see that the computational capacity of the system depends on how we formulate the input, how long the steps are and what amplitude there are. So the best capacity is with a fairly long duration of each input item, but a fairly low amplitude. And once again, we can see that we can shift it between linear and long memory, as shown in this top plot here, or more nonlinear and shorter memory, depending on the choices of the input, just the input duration and the amplitude here. And this converts to different computational performances. So here we're looking at two tasks. So we have an input that is just a series of high and low. And then we give it two tasks. One is a short-term memory task. So what was the input tau steps ago? And the parity task, which tells us, do we have an even or an odd number of high elements? And we calculate the performance as before and sum it up over the different delays. And so we can see that so the top row shows us the energy of the system. So for different choices of the damping strength. And then we see the short-term memory task and the parity task. So for the linear task, the best performance is far away from the stochasticity threshold, which is given by that red curve. And it's also best where the time scale of the input matches the time scale of the damping. And for the nonlinear task, the best performance is quite a lot lower than for the short-term memory task. So these be aware that the color coding is different between the three rows. But the best performance here is at or beyond the threshold. And what's interesting about this is that whereas this is perhaps not so relevant for understanding the brain, but if we're interested in neuromorphic applications, it strongly suggests the possibility of being able to tune the system for a particular task. So we can tune the material properties, and we can tune the input encoding to pinpoint a particular computational profile, or at least this is what we hope to be able to do. And this brings me to my final slide, where I'd like to say who did all the work here. So much of this work I did together with Renato Duarte, who's now at the Donders Institute for Brain Cognition and Behavior at Radboud University. The neuromorphic work was done together with Yuri Mokrosov and Daniela Pinner at the Peter Grünberg Institute at the Jülich Research Center, where I also am, and everything else was done by members of my group at the Jülich Research Center. So Barna was responsible for the modular networks with transmission. Tobias is responsible for developing this capacity measurement technique, and Marvin and Michael are responsible for all the simulations on the Fermi-Pascal and Siegel model. And with that, I am at an end, and I thank you very much for your attention.